So, do you have any question from the previous lab experiments? We worked on infiltration, hydraulic conductivity, soil moisture measurement, discharge measurement or flow measurement in open channels. And this, the sixth experiment or sixth learning you are here for flow measurement in pipe flow conveyance system. Pipe flow means it is flowing under a pressure. So it's a supply through pipeline where full pipe flow is there and it is under pressure. So we need to measure or find out what is the discharge. If we know the discharge of flowing pipe, we can immediately find out what is the total amount in a certain time t it has been diverted for irrigation purpose into the field. So in open channel, usually you have worked out or you have learned of using notches and weirs. So V notch and rectangular notch you have experimented last week, and this week it's a flow measurement in pipes by using two attachments, that is Venturi and Orifice. So it is called Venturimeter and Orificemeter. So these are used, very cheap arrangements, not costing much, of measuring flow in pipelines. So this is our target of learning today. So if you have any query from the previous learnings, you can ask me here, or let me tell you how we can do that for the measurement of flow system in pipes. So this is, I am sharing you my PPT first. Can you see the PPT slides?
Yes, sir.
Okay. So objective, what we can make for this learning, calibration of Venturimeter as well as Orificemeter. Calibration means we are developing a relationship here to find out the discharge. If we are simply measuring, say, a particular characteristics of flow, suppose head difference, head. If you recall the theory, we have Venturimeter and Orificemeter theory we have learned in our theory class. It is attached in a, say, pipe by using a flange here. So two pipes, and in between we are simply developing here either a Venturi which has a pipe, convection, throat and diversion. Conversion here, throat and diversion arrangement. So it is fitted here in between two pipes by using flange, or it is a simple plate of the same size or same diameter which has opening less than the pipe diameter. So this is a plate which has a cutted opening here of lesser diameter than the pipe diameter, and it is fitted in between. What does happen if we are reducing the flow area than the pipe diameter or pipe size? It will reduce the pressure, increase the velocity, because discharge is fixed. So this theory, which is governed by Bernoulli equation, it is used here. Simply, if you recall that learning of theory, here we have experiment to calibrate Venturimeter and Orificemeter by establishing the relationship between flow rate and pressure difference. So discharge versus head. Basically head, it is once it is throat or reduced opening, it changes the head with respect to head that is in pipe system. So if we are measuring the head between these two or comparing the head between these two, here head is reduced, here head is more. So difference in head, that is delta H, we can take difference. So it's basically head versus change in, discharge versus head difference in pipe and Venturimeter or Orificemeter condition. So if we are measuring this, simply we can make a relationship. So any future condition, we need to simply measure the head difference between pipe and the opening of orifice or Venturi throat to find out the simply discharge. Another condition is here. I will show you, or if you recall, we discussed this development of relationship in between these conditions, discharge and head difference. So there is condition of theoretical analysis or theoretical calculation of discharge versus practical. So because of practical condition, theoretical is multiplied by coefficient, that is called coefficient of discharge. So this is practical or actual versus it is theoretical. So CD. So in any relationship, we have generally a coefficient which is retardation coefficient or discharge coefficient. So the value of discharge coefficient or coefficient of discharge we need to establish for these two attachments in pipe flow system which are used to measure the discharge. So this is our objective. We will be certainly using fitted Venturimeter and Orificemeter in pipeline. So Venturimeter and Orificemeter fitted in horizontal pipeline with means of varying flow rate, so that for different discharge condition we can establish this relationship and find out the coefficient of discharge value. To measure the pressure head difference between the throat of Venturi and pipeline and orifice opening and pipeline, we are using mercury U-tube manometer. So it's a U-tube manometer you have already learned in your fluid mechanics classes, but simply here I will try to recollect you that learning. So U-tube manometer, if it is fitted in a pipeline system, simply here suppose it's a pipeline, it measures the pressure at the center of flow line by using a U-tube that is connected to this. So here it is, we are using a heavier fluid usually, or any fluid we can have of different characteristic than flowing fluid here. So here mostly mercury is used. So suppose pipe is flowing in this direction, this is discharge side, and if you are measuring the pressure head at these 2 points, neglecting the head loss due to friction, because these are 2 points very near to each other, we simply find out this is P1 pressure 1 and P2. So P1 is higher always and P2 is lower in simple pipeline. So because of its high pressure, mercury level will be somewhere here, and because of low pressure relatively there will be a difference in mercury level here, that is basically delta H we are measuring here. So this is U-tube differential manometer which is used in such kind of fitting to measure the head difference. Now if we have that idea, theory you have already gone through because I have sent you a write-up related to this experiment, and I hope you have gone through that to understand clearly about this experiment. So these two fittings in pipe flow system, Orificemeter and Venturimeter, are used to measure the rate of flow, that is basically discharge per unit time, and of the fluid that is flowing in pipe. What principle it uses? Simply it uses that reducing the cross-sectional area of flow passage, a pressure difference is created which enables determination of discharge through pipe. So this is basically the Venturi, and this is orifice. If you recall, we are developing this by using simple plate which is having lesser diameter of opening. So this is opening diameter and this is the complete plate in pipe flow system. So if we are measuring flow here as well as somewhere upstream here and comparing, because of reduced diameter, velocity is increasing. Suppose this is section 2, B2, and we are taking velocity 1. So B2 is greater than B1, but P1 is here greater than P2. Reason being P1 B1 is equal to P2 B2, that is usually following condition. And if we are using Bernoulli's principle, simply taking very near or it is negligible head loss due to friction, we can write the relationship between these 2 points where we are measuring the static pressure of pressure head. Simply P1 by rho g, that is in simple head of water, simply head section, plus velocity head is equal to simply at the second point, that is point 2 or section 2, P2 by rho g plus V2 square by 2g. Neglecting this head loss due to friction and having the same reference level of these 2 points. So Z is also cancelled out. Now if we want to find out measure the head difference, because it's a clear head difference, you can see here it is delta H basically. We can have P1 minus P2, that is simply equal to what? B2 square minus B1 square by 2g. Or simply P1 minus P2, that is our target, is equal to rho g into B2 square minus P1 square by 2g. Now you can find out what is the value of V. That is basically the equation here we are going to use, or the relationship. We learn into theory to find out this relationship. So P1 minus P2, that is simply B1 minus B2, that is equal to, here we can find out, or say we can write out V2 square minus B1 square is equal to 2g P1 minus P2 by rho g. And this particular relationship is equal to what? Head difference, that is here we have measured. That is delta H in terms of head difference. So we can write this relationship 2g delta H. And you know that, let me clean out here because you know it. You know it, that discharge is constant. Q is equal to A1 B1 is equal to A2 B2. So we can write here V2 is equal to simply A1 B1 by A2. Now replacing this relationship here, B2 square is equal to A1 square V1 square by A2 square minus V1 square is equal to simply 2g root H. Now we can as well write V1 square is equal to A2 square 2g root H by A1 square minus A2 square. Or say simply we can write V1 is equal to A2 root 2g delta H divided by root of A1 minus A2, here A1. So A1 square minus A2 square. This is velocity. So now find out the discharge. We can write from the same mass balance equation or conservation of mass. Q is equal to A1 V1. So here discharge, that is again theoretical because we are making a theoretical relationship. So Q theoretical is equal to how much? Multiply by A1 simply. So A1 A2 root 2g delta H divided by root of A1 square minus A2 square. Since it is theoretical, to find out the practical or actual or practical, whatever you write, it is simply multiplied by CD. And in this way, this will be equal to CD A1 A2 root 2G delta H divided by simply A1 square minus A2 square. So there are two conditions in this experiment. We need to establish the relationship between discharge and delta H, that is discharge versus delta H. To find out at any moment, if we know the delta H, we can say what is the discharge. And for learning to find out the value of CD, value of coefficient of discharge. So estimate the coefficient of discharge. If we measure the discharge somehow, that is coming out of the pipe CD, then can be estimated as Q, that is measured into A1 square minus A2 square divided by A1 A2 root 2GH. So making this arrangement for both, whether it's a Venturi or it's Orificemeter, we are simply finding out coefficient of discharge for both the fittings in pipes and establishing a relationship between discharge and head difference. Here as well, it is head difference. This is Orificemeter or orifice which is fitted. Because of this reduced opening of the flow passage, it will increase the velocity for the same discharge condition, which will enable to reduce the pressure. And if we compare these two pressure to find out the head difference, we can simply find out the discharge condition by this equation. So we need to find out CD value for both orifice and Venturimeter and establishing a relationship that is called the calibration curve or calibration of these two attachments with respect to delta H. That is our objective of learning. You might have seen here, this is not exactly the pipe we are simply cutting a hole, but it is having a kind of beveling towards downstream side. And this beveling angle is, our bevel angle is, our cutting angle is simply like this. We are developing. This varies from 31 degree to 45 degree for orifice plate. Here it is no way because it's a simple opening, but here it is a bevel angle of 31 to 45 degrees developed in orifice plate to reduce the resistance to flow to get better efficiency. So we need to find out what is the effect of such kind of arrangement in pipelines by finding out the value of coefficient of discharge and establishing the relationship between discharge and head difference that has been measured. Now, this is the theory. Venturimeter as well as Orificemeter. So this is the equation which is given in your supply write-up. You have gone. So either you take this A, capital A versus smaller a, or simply A1, A2, or it is called A0 sometimes A. It has the same relationship. So you can put this equation everywhere in such kind of differences in pipe flow opening. Now this is important. Orificemeter, again here it is written upstream face of the plate is beveled at an angle lying 31 to 45 degree. And this plate is clamped, you have learned in theory classes, between two pipe flanges with beveled surface facing downstream. So two pressure taps are provided, one on the upstream side and another downstream side of orifice plate. And in Venturimeter, one on upstream side in the pipe section and one in the middle of the throat section to measure the head difference between these 2 points. So once we know the theory, we know the arrangement, we know the technical condition, we can go for observations to find out the head difference with respect to the discharge condition in both the fittings to find out a calibration characteristics. And if we have interest to find out the value of coefficient of discharge, we can calculate back by using the information about the size of pipe diameter, size of the orifice or size of the venturi throat. In general, it has D by D ratio of 0.6. That D is the diameter of venturi or orifice opening, and capital D is the diameter of the pipe, and it has a relationship for our particular experiment set up in the laboratory condition 0.6. And the diameter of opening and orifice opening and venturimeter throat is 25 mm. So you just see the experiment setup in the video I am going to give you. You have gone through the methodology of working, or you can understand a little bit what it is shown in the video. Then I will give you these observations. Venturi size in terms of pipe diameter, size ratio of D by D, small d by capital D. You can find out the cross section area of pipe and opening, venturimeter throat and orifice opening. We have yes, one important aspect, when it is flowing through this orifice or venturimeter, we are simply collecting this discharge, that is Q, in a tank of size 40 centimeter length and 40 centimeter width. We have arrangement of this stilling basin or graduated scale to find out how much is the head it has collected in the tank, or depth of water is collected in the tank for a specific time, that is T. So starting from a point here, that is say H1 in this scale to H2, so difference in height of water collected in T can be used to find out the discharge per unit time, because we know the dimension of the tank 40 centimeter by 40 centimeter, and this H, if we are multiplying, it can be transformed into cubic meter, and if divided by T, it will be cubic meter per second unit of the discharge that can be used. So this is basically the arrangement in the laboratory, and a video I will show you here. I will upload it in your files, so you can see that. And then here observations I will provide you for left hand, that is basically the inflow side of the supply line, and right hand head, that is basically on the venturi throat or at the just after flowing through orifice meter. So these are two heads measured in this system by using U-tube manometer, and both the observations are there. You can find out the delta H. This is the discharge that is collected in the tank, initial height of the water in the tank, final height of the water in tank. You can find out the head, that is our height, that is discharged through this flow in time T. You can find out discharge per unit time to calculate the coefficient of discharge, that is CD, for both the condition venturi and orifice meter. Finally, you can calculate the average value of coefficient of discharge for orifice as well as venturimeter. And at least remember this, there I am going to give you 3 observations, but it should be at least 5 observations to get more accurate information about the coefficient of discharge. So you can show your result in terms of discharge corresponding to head difference in a log paper to make the linear relationship and to find out the calibration curve between head versus discharge and average value of CD for orifice as well as venturimeter. So this is our objective of learning today, to measure the discharge in pressurized pipe flow system. Any query if you have? Students?
No, sir, no query.
Okay. Then if there is no query about the theory and learning, here it is your video. Can you just see the video? Download the video in file section, uploaded file section. Class material.
Yes, sir. Yes, sir.
So there is experiment 6, calibration of Venturi and Orificemeter at the last. Can you just see and tell me whether it is working? I think this is for 15 minutes.
Yes, sir. It is. It is working.
It is working. So it's just 301. Let us meet at 3017 or 317. Right? It is near about 14.5 minutes or 15 minutes maximum. So can you please watch this video and tell me if there is any problem of understanding or any query comes to your mind? And then I will upload here experimental observations to learn the experiment and to find out the CD value, as well as developing a relationship or calibration of orifice and venturimeter versus head difference. Is it okay? Let us meet at 317.
Okay, sir.
Okay. Okay. So now this is the last experiment on minor head losses, as well as the most important aspect of this is to measure the flow in a pipe supply system or pipeline. So what we use Venturimeter and Orificemeter, or Venturi and Orifice, to measure the discharge basically. If you are going towards the objective of this experiment, we have two objectives. Find out the coefficient of discharge, as I told in theory, coefficient of discharge CD, because practical and theoretical discharge because of this abstraction will change. So finding out coefficient of discharge of Venturi and Orifice, and find out a calibration relationship or calibration curve between discharge and head that is created because of this change in size of opening, because pipe, it has reduced size. So because of change in size or change in diameter of flow, it changes the pressure condition, it reduces the pressure, increases the velocity at both. So because of this change in head, we can measure or we can estimate the discharge of flow. So we need to calibrate. Calibrate means discharge versus difference in head relationship, one thing, and find out the coefficient of discharge. That is basically once we are changing the diameter of flow pipe to venturi or orifice, it reduces or increases the velocity and reduces the pressure. So this relationship here we are using to find out the coefficient of discharge and calibration relationship between these two. So let us see how we are doing. So there is one supply pump. It is supplying water from here to these two conditions which are governed by these two openings. If we want to go first for venturi, we are opening this, closing this, and the discharge which is coming through this venturi, we are collecting in this tank. Tank has a defined dimension, length and width, and we can find out how much head of water or discharge it is collected in this tank per unit time, or say simply time versus height. So volume versus time we can find out, or for a particular head or particular time we can measure the discharge that is coming out from these two. So at least for 5 different discharge condition. If we are taking the observation, we can find out the calibration curve or relationship between discharge and head difference, that is measured by using U-tube manometer here, mercury U-tube manometer. So we have this mercury U-tube manometer is connected with supply side. So we are simply measuring the head difference by using U-tube manometer. In this arrangement, we can find out coefficient of discharge and calibration relationship. Okay, so let us measure the size of this tank which is collecting the discharge. This has size of 40 centimeter length, we can say. It has 40 centimeter width as well, and you can measure the discharge in terms of head, that is increasing per unit time, by seeing this scale, that is a stilling basin arrangement. So this is the discharge measurement, and now you can measure the head difference by using U-tube manometer. So this is connected from outside, this is outside connected limb, and this is inflow connecting limb. So it has more pressure. Usually you will see when it is running high pressure this side. Once high pressure this side, it will go down and low pressure will go up. So you can see these arrangements. U-tube manometer you have already learned. So in this arrangement we can find out what is the pressure difference and what is the head that is discharging per unit time, and we can find out the coefficient of discharge by using the same relationship. Discharge is equal to CD A1 A2 into root 2 GH. H is the head difference, basically left and right limb, and divided by root of A square minus A1 square minus A2 square, means before or the size of the pipe versus size of the opening of Venturimeter and Orificemeter. Started first through Venturi. So it's the supply of water through Venturi, and flow is here. It is discharged. So when we are measuring, we will shift this to here, otherwise we can bypass it. And let us see, because it's stabilized the flow now, full flow condition of this pipe. Let us measure what is the head difference between supply side and Venturi throat, at the Venturi throat. So it is supply of the water to measure the head. It is open when it is parallel to supply line, and this is basically U-tube manometer, which is used to measure. Now you can see if there is any air bubble. So you can see there is no air bubble, water is coming out from the root of the tube. Okay. Now it is closed, and now you can see here it is the difference in head, and this is supply side having more pressure than the discharging side, has less pressure. So let us measure what is the head from supply side. This is 2.6, and here this is 9.4. So 2.6 and 9.4 for one supply condition, and let us measure the discharge for this. Closing this. This is supplying water here, and you can see the moment it is here. It is here. We have timer. So let us come here. Let us start from 4 now. 4 to 14 means 10 centimeter rise of water. How much time it takes? Because we know the dimension of this tank, so we can find out the value for this 10 centimeter rise, 4 to 14, and time we are recording, so we can find out the discharge from this setup. Okay, so now it is 14. So it is 25.89 seconds. Let us take one more reading. So now you can see we have changed the discharge condition. So now this is the second head condition. At the supply side it is 4.3 and discharge side it is 7.8. So 7.8 and 4.3. 4.3 is supply side and 7.8 is discharge side. So that is head difference in second discharge condition. And now let us measure how much time it takes to fill the tank. Again starting from, say now this time, so let us take from 2 to 12. So let us take from 2, the moment it reaches to 2 centimeter head, we will start. It is at 1 and now it is 2. Start. So 2 to 12. Let us see how many seconds it takes to reach to 10 centimeter head of water in this tank, which has dimension 40 centimeter by 40 centimeter. Okay, it is 8, 9, 10, 11, and now reaching to 12. So it is 37.15 seconds it took to reach or increase 10 centimeter discharge. So now we have connected this Orificemeter, which is supplying water from inflow side as well as outflow side to this U-tube manometer, and it is now stabilized discharge condition or supply of water is almost constant. So let us measure the head difference for this discharge condition first, and after that we will measure what is the discharge. So head at supply side it is more fluctuating condition for Orifice, that is 3 somewhere 4 to 8.5 or 8.6, 3.4 and 8.6. That is the head difference. And let us measure what is the discharge. Again let us see, for 10 centimeter increase of head in this tank, starting from 1 to 11, or let us start from 2 to 12, because that is more visible and there are less chances of error. So it reached to 2. Now let us see. So 2 to 12. Now nine, 10, 11, and 12. So it is 36.49 seconds. So now change the discharge from here a little bit, okay, and let us see how. Okay, let us see for the second discharge condition, that is coming from Orificemeter or Orifice. So head let us measure for different second discharge, that is 2, 2.2 supply side, and discharge side it is 9.7. So 2.2 and 9.7 are the head from supply and outflow side, and let us measure the discharge that is coming through this, and let us again take from 2 to 12 so that there are least chances of error. So it is now 2. So starting from 2 to 12, let us see how much time it takes to find out the discharge condition of this setup to estimate the coefficient of discharge from Venturimeter. Coefficient of discharge of Venturimeter. So it is 11, now it is 12. So it is 27.64 seconds. In this way, I will observe for at least 5 discharge conditions, the head difference by both Venturi as well as Orifice, so that you can have a calibration relationship between head and discharge, as well as you can estimate the coefficient of discharge for these two setups in pipe flow system. Okay, thank you. So, is it over? Have you seen the video? Students?
Yes, sir.
Yes, sir. Just complete.
Okay. Yes, sir.
So any query if you have? Any query? Otherwise, observations are updated, are uploaded in your file section. You can see that files, those are uploaded in class material. Can you see it?
Yes, sir.
Is it there? Okay.
Yes, sir. Yes. Check.
So basically observations I have given. Diameter of main pipe it is given, D by D ratio it is given, tank size is given 40 centimeter by 40 centimeter. That is very clear from the video as well. Here it's right limb is written first, so it's H1 and H2. You can see it here. You can find out the head difference. And the important aspect here is in this observations, if you just see here, let me share you. Here, these are observations. It's multiplication of 12.5, 12.6, sorry. Can you guess how it is? It is simply the measurement. In YouTube manometer, if you recall, it is unstable condition. Here, let me take this space. So it is YouTube manometer. If we are trying here, it is connected to a horizontal pipe. Just take a horizontal condition, right? And we have this delta H. You recall P1 minus P2. Here it is P1 in section 1, it is P2. That is simply, if we are analyzing this P1 and P2, so P1 is equal to how much? This is H1, suppose this is H2, and this difference between is delta H. So P1 is equal to, or at this first one, the pressure at this point at section 1 is P1, that is pressure head, plus this displaced condition. And if suppose it is flowing fluid is of density rho G, and it is H1 that has displaced this fluid, which is used in H tube manometer, this one. That is equal to the section 2 What is that? P2. We are simply measuring at the second point pressure P2 plus what is here? To make this equal, this level of reference we are taking. So it is equal to at H2 rho G H2 plus the second condition, that is rho Hg, because it's mercury which is used, G into delta H. So if we are finding out pressure difference between P1 and P2, it is simply rho G, this H2 minus H1, it is going another side, plus rho Hg into G into delta H. Now you know that H2 is simply H1 minus delta H. Sorry, H1 is H2 plus delta H. H2 is H1. H1 is H2 plus delta H. Here we want to replace. So rho G into H2. What is H1? Minus H2 plus delta H. So minus delta H plus rho Hg G into delta H. Now you can find out this as rho G delta H, that is minus, because it's minus, plus rho Hg G into delta H. Here you can see that P1 minus P2 is simply what? G into delta H rho Hg minus H, simply here. Sorry, rho Hg minus rho here. And rho Hg is 13.6 minus, for water it is 1. So that makes 12.6 G into delta H. And this is simple equivalent condition. To make this water head, this is pressure difference in Newton per meter square. To make this in head terms of water, 12.6 G into delta H divided by rho G again. So rho value is 1 here, and G, if you cut this here, it is simply 12.6 into delta H, that is given here. Head loss in terms of water head with respect to mercury, because we use in YouTube manometer liquid as mercury. So in this way you can find out head difference in terms of water head for this, and you know the discharge condition, that is from taken initial to final head in this graduated tank, volume collection or flow collection. We can find out what is the discharge if we have observed the time. So if you know the discharge, you know the delta H condition head, we can find out the value of CD. So this is the exercise we need to perform for learning this calibration of Orifice and Venturimeter, and to find out coefficient of discharge value for these two. Any query? Students?
No, sir.
You were sleeping or you were out? I couldn't understand.
No query.
No, sir.
Okay. Okay, then you complete and submit by Friday midnight. Oh, sorry, Saturday midnight. You have taken. And this is the last. This is the last experiment before midterm. It is called midterm. So next week it will be test come viva for theory and lab classes. Is it okay? And tell me day after tomorrow what timing you prepare to viva voci and test, class test, theory test, and viva voci for lab experiments. Okay.
Yes, sir.
Okay. So complete this and let me know what you have learned in next week. Is that right?
Yes, sir. No problem.
Okay. Okay. You can have.
Thank you.
With your learning, and they will meet Wednesday for theory.
Thank you, sir.
Okay, welcome.
Thank you.
Thank you, sir.
Okay. So still there are 20 students. What are they doing? Okay, Rajesh.
Yes, sir.
You can go. I have sent you the attendance of the students
Okay.
today. You update please there as well. Okay. See you then. Bye.